Hi everyone. Today we are discussing the third part of kinetics. In this, we are discussing the concepts such as complex reactions, that is kinetics of reactions other than elementary reactions, then pseudo-order reactions, and influence of temperature on rate of reaction, that is Arrhenius theory. And also we will discuss some concepts, some basic introduction to enzyme catalysis. First of all, let's see what is pseudo-order reactions. So these are the reaction in which one of the reactants is in large excess and it shows an order different from the actual value. So in certain reactions, we expect a particular value for order, but the actual order will be different from the expected value. So such reactions are called pseudo-order reaction. So for such reactions, the experimental order is not the actual order, and for elementary reactions, we know molecularity and order will be identical. Elementary reaction means single step reaction. So for such reactions, order and molecularity will be mostly same. So pseudo order reactions are also called pseudo molecular reactions. Now let's see one of the examples of pseudo order reaction. The hydrolysis of an ester, that is an example for pseudo-order reaction, and the rate law expression for this hydrolysis of ester we can write as rate constant into concentration of ester into concentration of water. Here we have taken ethyl acetate as the ester, and here in this case in the ester hydrolysis, the concentration of water or water is present in large excess, and because of that the concentration of water can be kept as a constant. So for example, if we take 100 ml water and the volume of ester taken will be somewhat 5 ml. So compared to the volume of ester, the volume of H2O will be in large excess so that its concentration remains more or less constant. So we can rearrange this rate equation as rate is equal to K dash into concentration of ester CH3COO C2H5, where K dash is a new constant which is equal to K into concentration of H2O, because these two are constant, and now that on multiplication gives a new constant K dash. So we can see that from the rate equation, the rate of reaction depends on the concentration of only one species. So the reactions follows first order kinetics. So the reaction seems to be second order, but it actually follows first order kinetics, and such reactions are called pseudo order reactions. That is a reaction in which one of the reactant is in large excess and hence shows an order different from the actual value. Next we can discuss complex reactions. Complex reaction means reactions which proceed in a series of steps rather than single step. So reactions other than elementary reactions are called complex reaction, where we can see multiple steps rather than more than one step will be there for the reaction, and these are called complex reaction. Some of the complex reactions are opposing or reversible reaction, consecutive reaction, parallel reaction, and chain reaction. So these are some of the examples of complex reactions, and now let's see each one in detail. So first let's see opposing or reversible reaction. So as the name indicates, these are reversible type, or the reactions in which the products formed react to give back the reactants are called reversible or opposing reaction. So if A is reacting to give a product B, that B will react back to give the reactant. So for such reaction, we can have two rate constant. A rate constant for forward reaction and rate constant for backward reaction. If we write rate constant of forward reaction as K1, we can say K minus 1 is the rate constant of backward reaction. So for such reactions, we know initially the rate of forward reaction will be very large because initially we have only the reactants. But with passage of time, more and more amount of products are forming, then slowly some of the products react back to reactant. So that means the rate of forward reaction decreases and also the rate of backward reaction begins to increase. And this continues until a point is reached where the rate of forward reaction is equal to the rate of backward reaction, and this condition is called equilibrium. So if we do not change any of the variables of the system, the rate of forward reaction and backward reaction becomes equal at equilibrium, and at equilibrium we can say the overall rate of the reaction is 0. That means the reaction, it seems that there is no reaction going on, but actually there is a reaction in the forward and backward direction at the same rate, so that net rate will be 0. So here we can see A giving reversibly giving B, and K1 is rate constant of forward and K minus 1 is the rate constant of backward reaction. So here also we can say at time t equal to 0, let A be the concentration of reactant. A be the initial concentration of reactant at 0 time, and after a time t, if X amount of product has formed, we can write rate expression, that is instantaneous rate, dx by dt equals, first of all we have to consider forward reaction, that is K1 into A minus X, that is formation of B. K1 rate constant into starting concentration A minus X after a time t. And we know this B, even though B is forming in the forward reaction, it is reacting back, or it is decomposing in the backward reaction. So we have to write minus of K minus 1 into, then we have to consider the B giving A. So K minus 1 rate constant into starting concentration, that means concentration of B, that will be X. So this is the rate equation, dx by dt equals, we can write rate constant into starting concentration. So for forward reaction K1 into A minus X, and for backward reaction we have to write minus K minus 1 into X. Here we take X because here the reaction is B giving A. Backward reaction is B is giving A. So there the starting concentration is that of B, which is X at a time t. So this way we can write the rate expression for opposing or reversible reaction. Second type of complex reactions are consecutive reaction. So consecutive reaction means reactions which proceed through more than one step. So we will have intermediates in this consecutive reaction. For example, in this case, A giving B and B is giving C. So here the reactant is A and the product is C, but A is not directly converted to C, rather there is an intermediate B. So here we have two reactions or two steps with two rate constants K1 and K2. So here also we can write at t is equal to 0, at 0 time, that means initially if we have A amount of A, that is small a amount of the reactant A, and at that time at t equal to 0 we don't have any B and C, so concentration of B and C will be 0. After a time t, let X be the concentration of A, Y be the concentration of B, and Z be the concentration of C. So we can write the rate of formation of B, or we can also say the rate of decomposition of A. Rate of decomposition of A equals rate constant K1 into X. Starting concentration is X. So rate of decomposition we usually write minus dA by dt. Minus d by dt of concentration of A, that is equal to rate constant K1 into starting concentration at time t, that is X. And we can write rate of formation of B. Rate of formation of B, d by dt of concentration of B, that is equal to, we have two steps or two reactions involving B. One is formation and other is decomposition. So formation we give plus sign, decomposition we give minus sign. So we have to write rate is equal to rate constant into starting concentration. So we can write rate of formation of B is equal to K1 into X. B is forming from A and that rate is K1 into X minus K2 into Y. B is decomposing in the second step where the starting concentration is Y. Y is changing to Z. So we can write rate of formation of B equals K1 into X minus K2 into Y. We can also write rate of formation of C. C is involved in only one step, that is B is converted to C. That is C is forming from an amount Y amount of B. So that rate of formation is equal to rate constant K2 into Y. So this way we can write the rate expression, and in this case for any consecutive reaction the overall rate of a reaction depends on the magnitude of K1 and K2. Since we have two rate constants, the overall rate, net rate of the reaction depends on the magnitude of K1 and K2. Suppose K1 is very greater than K2. That means the first step is very fast and second step is slow. So in such a case, the second reaction controls the overall rate of reaction. We know when we have multiple steps, the rate of reaction or rate determining step will be the slowest step. The slowest step will determine the rate of reaction. So if K1 is very greater than K2, that means first step is fast, so the rate determining step will be the second, or we can say this conversion of B giving C will control the overall rate of reaction. And instead, if K2 is very greater than K1, that means the second step is very fast than the first step. So the first step, conversion of A giving B, will control that reaction, will control overall rate of reaction. And suppose if K1 and K2 are of comparable magnitude, then the overall rate of reaction depends on both values, both K1 and K2. One of the example for consecutive reaction is the hydrolysis of diesters. Diesters undergo hydrolysis in two steps. In the first step, one of the ester part will be hydrolyzed into acid and alcohol, and in the second step, the second ester unit will be hydrolyzed. So that is an example for a consecutive reaction. The third type of complex reactions are parallel or side reaction. In parallel reaction, the reactant molecule decompose in different ways giving different products. So we have more than one steps and it will give more than one product. So such reactions are called parallel reactions. And for example, you have A giving B and C in two different pathways. Let K1 be the rate constant for one pathway and K2 be the rate constant for second pathway. And if K1 and K2 are of appreciable or both are of similar magnitude, then we can say the two reactions are parallel reactions. So here one of the example for parallel reaction is the nitration of phenol. Phenol on nitration we get orthonitrophenol and paranitrophenol. Here both products are forming in almost equal quantity. So that is an example for a parallel reaction, and for this parallel reaction we can say the rate of formation of B. So for that, if the concentration of reactant A is X, suppose it is X, so the rate of formation of B is equal to K1 into X and rate of formation of C is equal to K2 into X. So that is parallel reaction. That means the reactant give more than one product in more than one step. And the next type of complex reaction is the chain reaction. We are quite familiar with chain reaction. That means free radical reactions. Free radical assisted reactions are mostly chain reaction. So these are the reactions in which highly reactive intermediates are formed and they carry on the reaction at a rapid rate for a longer period of time. So such reactions which once it is initiated, it occurs at a faster rate for a longer period of time. Such reactions are called chain reaction. One of the example for a chain reaction is the photochemical reaction between H2 and Cl2 yielding HCl. So here it is light assisted, photo assisted conversion of H2 plus Cl2 giving HCl. So now let's see the different steps in a chain reaction. First step is the chain initiation. Chain initiation means we'll have the formation, generation of reactive intermediates or radicals. So here the chain reaction, as I said, most of the chain reactions are proceeding through free radical mechanism. So free radical means these free radicals are generated by the homolytic cleavage of a bond. So here we know Cl2, it is a homonuclear diatomic molecule, and this bond undergo homolytic cleavage. That means each atom gets one electron each. So two chlorine radicals are generated. We have two types of bond cleavages that we know, homolytic and heterolytic cleavage. Heterolytic cleavage results in ion pair. We get cation and anion as a result of heterolytic cleavage, while homolytic cleavage results in radicals. Anyway, in the first step of chain reaction, we get two chlorine radicals. The second step is called the chain propagation. That means the free radical will initiate the reaction and that chain will propagate. So here the formed reactive intermediates react with neutral molecules to form new radical. So the initially formed radicals are consumed and new radicals are generated. That means in this example, in the given example, the generated chlorine radical attacks the hydrogen molecule and forms HCl and hydrogen radical. So this hydrogen radical can capture another chlorine molecule, neutral molecule, to give HCl molecule plus Cl radical. So this randomly combine with the neutral molecules to give various neutral molecules and new radicals are generated. And the last step is called chain termination. Chain termination means it is the quenching of the reactive intermediates. That means the free radicals combine each other to form neutral molecule. So two hydrogen radicals can combine to give H2, two Cl radicals can combine to give Cl2, or one H radical and Cl radical can combine to give HCl. So for this free radical reaction, these chain reactions, once initiated, we do not have any control over the chain reaction. So that is the mechanism of chain reaction. We have three steps. First step is the chain initiation where radicals are generated, and second step is the chain propagation where initially formed radicals are consumed and new radicals are generated which will propagate the chain, and finally chain termination. The radicals combine each other to form neutral molecules. Next, we can see the influence of temperature on reaction rate, that is governed by the famous Arrhenius equation. We know temperature is having a significant influence on the rate of a reaction, and an increase of temperature is found to increase the rate of reaction. Usually we can see that with rise in temperature by 10 degrees Celsius, the rate of the reaction increases by a factor of 2 or 3. That means if you increase the temperature of a reaction by 10 degree, the rate may double or it become 3 times. So when we take the ratio of rate constant of a reaction at two different temperatures differing by 10 degree, that ratio is called temperature coefficient. So temperature coefficient means it is the ratio of rate constant of a reaction at two different temperatures differing by 10 degree. For example, you can conduct a reaction at 25 degree and you can measure the rate constant as K1, and the same reaction you can conduct at a temperature 35 degree and that rate constant be K2. Then the ratio of K2 by K1, that is called temperature coefficient. And a more convenient relation between temperature and rate constant is given by Arrhenius equation, and Arrhenius equation is K equals A e raised to minus EA by RT, where K is the rate constant, A is called Arrhenius factor or pre-exponential factor, EA is the activation energy and T is the temperature. So this is the Arrhenius equation, exponential form of Arrhenius equation. Now, when we have two temperatures, when a reaction is conducted at two temperatures T1 and T2, and if the rate constants are K1 and K2 respectively, then the relation between these, the rate constants and the temperatures, can be given by the logarithmic form of Arrhenius equation, that is log K2 by K1 equals EA by 2.303 R into T2 minus T1 by T1 T2, where K1 is the rate constant at temperature T1 and K2 be the rate constant at temperature T2, and EA is the activation energy. Now let's see the concept of activation energy. We know a chemical reaction, in order for a chemical reaction to proceed, the reactants must possess a minimum amount of energy. You can see the figure. In the figure, we have reactants at a particular energy and products at a lower energy. So the reactants cannot directly come down to the product energy. Rather, it should cross an energy barrier in order to form the products. So this energy barrier has to be crossed by the reactant to decompose to product. So this energy, the amount of energy at the peak of the barrier, that is called threshold energy. So we can say, for a reaction to take place, the reactant molecules must acquire a minimum amount of energy, and this energy is called the threshold energy. So the reactant molecule must cross this threshold barrier to decompose to the product. But however, most of the molecules do not possess this threshold energy. So we have to provide energy externally by means of heating, or by other means we can externally provide the energy. So that excess amount of energy over the energy possessed by the molecule, that excess energy is called activation energy, represented by EA. So we can say activation energy is the excess energy that the reactant molecules must acquire in order to react to give products, that is the activation energy. So it depends upon the energy of the reactants. If the reactants have very low energy, we need to provide high activation energy. So activation energy is equal to threshold energy minus energy possessed by the molecules. So here, if we are using a catalyst in this case, what the catalyst perform is, it reduces the threshold energy barrier, or we can say it provides an alternate path with a lower activation energy, so that more of the reactants can now take part in chemical reaction to give the products. Next we can discuss enzyme catalysis. We know enzymes are biological catalysts which catalyze reactions taking place in living cells. So we can say different organic reactions taking place in the living beings are catalyzed by organic substances called enzymes. So they are complex protein molecules and are derived from living organisms. Each enzyme can catalyze a specific process, and this catalysis is called enzyme catalysis. And one of the main property of enzymes is their high specificity. They are highly specific in nature. That means an enzyme used for a particular substrate can fit only for that substrate. For a different substrate of the similar type, it cannot work. For example, here one example is given. The hydrolysis of urea, NH2CO, NH2, undergo hydrolysis to give ammonia and carbon dioxide by the enzyme urease. Now, in this reaction, if one of the hydrogen in urea is substituted by a methyl group, we get N-methyl urea. And if we use the same enzyme for the hydrolysis of N-methyl urea, we don't get the product. So that means the enzyme reactions are highly specific in nature. They will fit for a particular substrate only, and they are more specific than inorganic catalyst. And also, for the efficient working of enzymes, it need an optimum temperature and an optimum pH. Optimum temperature means the range of temperature at which the efficiency of enzymes are maximum, and optimum pH is the range of pH at which the efficiency of enzyme is maximum. So in order for better performance of enzymes, they need an optimum temperature and an optimum pH. So these are the things we have discussed in this video. We have first seen pseudo-order reactions, then we have seen the kinetics of complex reaction. We didn't go to the details of kinetics part. We have just seen what are different complex reactions and the rate equation for them. The various complex reactions such as opposing or reversible reaction. Then we have consecutive reactions, parallel reactions and chain reaction. Then we have also seen the influence of temperature on reaction rate and Arrhenius equation, and some introduction to enzyme catalysis. So thank you all for watching. Hope you understood.